derivatives and how you could take the derivative of the derivative of the derivative and keep going. So if I were to ask you for the second derivative of this, two derivatives, what you would do is you would do this first, then you do this, right? And get to here. Here's where you would do the derivative again, okay? But I haven't talked about what happens if there's a number in front, which I'm about to, okay? So there's advantages to leaving it in this notation, because if we're doing calculus and derivatives, and in Cal 2 antiderivatives, the opposite of what we're doing, that's what we do in Cal 2. You know how right now I'm giving you a function, we're taking its derivative? At the end of this class, in most of the first third of Cal 2, all you do is try and see if you can go backwards. Start with the function and go backwards from it. Okay, let's do another one. How about this one? This rule seems very simple, but there are some things that can become a little complicated with it. So you just have to make sure you've kind of addressed a lot of the different issues. What about this? What's the derivative of 1 over x? All right, the rule we have allows us to take the derivative of x to a power, right? Does this have a fraction in it? Does it say 1 over x to a power? No, it just says x to a power, right? We have to, before we use the rule, we have to make that look like x to a power. So x to the negative 1. You have to bring that x up, right? Back up into the numerator so it looks like x to a power, and then you can use the rule. Be very careful though, because n is negative 1, right? N is negative 1. Bring it out front, taking the derivative now, negative 1. X to what power? Negative 2, right? Because you're doing the negative 1 and you're subtracting 1. And negative 1 minus 1 is negative 2. So I have a negative 1 in front, which I'm just going to write as a negative, and then x to the negative 2. That would be correct, but I could also write it like this. To be honest with you, this comes up so much you should probably just remember that one as well. The derivative of 1 over x is negative 1 over x squared. So I'll just put a star next to a couple of stars. I guess what I'm saying is the sooner you memorize these, the ones that are starred, the sooner you memorize those, the easier your life is going to become as we proceed. All right, what about this one? What's the derivative of 1 over x cubed? See, take 30 seconds. See if you can figure that out. It's not a trick question. You got it? Yes? What is it?
1 over x to the fourth.
I agree that there's an x to the fourth on the bottom. You're missing something. Negative 3. Okay, so this is really x to the negative 3, right? And you're bringing out the negative 3, and then you're doing x, and you're subtracting 1 from that, you get negative 4. And then you can drop that down. I'm going to put the negative 3 on top and just put x to the fourth on the bottom. Negative 3 over x to the fourth. Okay? How about this one? What's the derivative of 1 over the 5th root of x cubed? Careful. Okay, negative. So first thing you have to do is rewrite this as 1 over x to what power? 3 over 5, right? 3/5. And then you need to bring that up. So this is x to the negative 3/5. Look, you'll see I'm not taking the derivative yet, right? I'm just rewriting this algebraically first. Rewriting it from radical notation to rational exponents, bringing it up, and now at this point I have x to a power, so now I employ the rule. The rule says that this will become negative 3/5 comes out, x, I'll take my time, negative 3/5 minus 1, right? So you have to rewrite that 1 as a what? 5 over 5. So what does that give you? When you take negative 3/5, what is it? 8/5, negative, right? X to the negative 8/5. I'll just leave it like that. I'm not going to drop that down and rewrite it in radicals. Okay? You feel like you got it? It's a great rule. I mean, this is the way it evolved, right? Newton was trying to figure out the slope of a tangent line, started to do it for specific functions, had this definition he came up with for the derivative. It was a limit. Then he started to say, wait a minute, can I make this more general? Can I do this where I don't have to do this limit over and over and over? Can I develop these rules? And that's where we are, all right? How about this one? I'm going to give you a function, f of x. Here it is. You know what? Hold on. No, we're not ready. Let's go to the next rule. Not ready for that one. That's the power rule. We're on rule number 4. There's 82 rules. No, I'm kidding. All right, so the next one is, I'll tell you what it's called first. It's called the constant multiple rule. So notice we had a rule earlier called the constant rule, right? This is called the constant multiple rule, which is a little different than the constant rule. We all know that the derivative of a constant is 0, right? What this says is, what if you have a constant in front of a function? Okay, which is the question you were just asking, right? So what if we have the derivative with respect to x of some constant in front of a function? Now look at this notation. This is weird. This is very general. I'm saying I have a constant times some function. I'm not telling you what this function is. This function might be x squared. This might be the square root of x. It might be any of the things I've given you, but with a number in front of it. This rule says that this is just the constant times the derivative of the function. That's the rule. I'm not going to prove it, all right? Y'all are just going to take this one on faith. I could prove it, it's going to take too much time. So this is saying, what is this saying? That if I have a constant in front of a function and I want the derivative, that the constant's just going to go out front, and then I will take the derivative of the function separately and multiply the answer. Right? So the constant doesn't go to 0, does it? Not when it's attached to a function. If it's just a constant by itself, the derivative is 0. But if you attach it or multiply it times some function, then what it does, what I will say in this class from here on out, is that the constant comes for the ride. Right? You'll hear me say that. The constant is going to come for the ride. It's just going to be there with us throughout the differentiation process. So let's do an example. What if we wanted the derivative of 4x squared? So the 4 is in front of the x squared, right? That's a constant in front of a function. According to this rule, what I'm going to do is bring the constant for the ride and then just take the derivative of the x squared, right? That's what this rule is exactly saying. Bring the constant and then take the derivative of that function. And we know the derivative of x squared is 2x. We did that earlier, right? And that 4 and the 2 can multiply and become 8. So 8x. Okay? Now, you will get to a point in this class where all you do is this. You bring the power down. 2 times 4 is 8, right? and then you do the power, reduce the power by 1, you get x to the first power. That's where you really want to be. But I'm just showing you the little pieces of how this works, right? Ultimately, power just comes down, multiplies times that number, and then you take the derivative. All right, or you subtract 1, sorry.
So if it was 4x squared minus 4, it'd still be 8x, correct? Right. The constant will go to 0?
The answer is yes, but I haven't told you that yet because I have not told you that when you subtract two functions that you can do something like that. I haven't told you that yet. That is going to be the case, but you can't assume anything in calculus. These things have to be established and the rule has to be proven, then we use it. You know what I mean? You asked me if you had 4x squared minus 4 and you took the derivative, that this would still be 8x.
Yes, sir.
So what you did is you said, I'm going to take derivative of this one, that's 8x, and the derivative of that is 0. But are you allowed to take the derivative of these separately? That's the question, right? The answer is yes, you will, but I haven't told you you can yet. You can't assume you can, unfortunately. Which is what's going to cause us the biggest problem, okay? That's going to be the biggest problem in this class, is that that works for addition and subtraction, but it doesn't work for multiplication. You'll see. All right, you ready? I'll give you another example. How about this one? How about 1/4 x to the 4th? What's its derivative? X cubed, x to the 3rd power. Right? Constant comes for the ride, or you can just say, hey, look, that constant's attached. I'm going to bring the power down. 1/4 times 4 is 1, right? And then x, you bring the power down by 1, you get x cubed. Is that all right, everyone? Okay, I'm not going to do any more with the constant multiple rule. I'm going to go to the next rule, 5th rule.
How many rules are there?
Let's see. We have the, yes?
I still don't get this.
Okay, hold on. Let me answer this question first. We have, what are we on? What rule are we on? 5? Okay, so we're on the 5th rule. Then we have 6, 7, 8.
This was 4.
Yeah, no, but the next rule is 5, right? And then 6, 7, I think it's 7 or 8.
I'll see.
Yeah, it's not much more, but the last two, no, yeah, the last 3 are going to be the ones that cause Cal students to have trouble. Yeah, yes?
So I still don't understand the process.
What do you mean the process? Like, if I have I have a constant, right? Being multiplied times a function. So this is c, and this right here is some f of x, some function of x. The rule says that if I want to take the derivative of that, all I'm going to do is write down the constant, okay, there it is, and then then I'm going to take the derivative of that function. The derivative of this function is 2x. The 4 is still here, it comes for the ride. Multiply the 4 and 2 and get 8. Yes? Here I did the same thing. I just did it faster. The 1/4 came for the ride. Then I took the derivative of this, which is 4 times x cubed, and then the 1/4 and 4 came together, canceled out, and became 1 in front of x cubed. That make more sense?
Yeah.
Okay. All right, the 5th rule is the sum difference rule, okay? The sum difference rule. I'll put difference, so you don't think differentiate. Sum difference rule. And here's what this rule says. If you're trying to take the derivative of some function of x plus or minus, it doesn't matter if this is addition or subtraction, okay? In either case, and you're adding it or subtracting some other function g. So you got 2 different functions that you're either adding or subtracting. This rule says that you are allowed, yes, you are allowed, to take the derivative of each of them separately. Okay, you're allowed to differentiate them separately and just add or subtract the 2 answers. That rule can be proven using limits. You can prove this is true. I'm not going to. But this is a great thing for us, okay, because it's telling us that the derivative behaves the way we hope it would behave. That when you have terms, you can differentiate them term by term. Term by term. So, and also, if this works for two functions, it also works for 3 or 4 or 5 or 6. Doesn't matter how many you have, you can always just take derivative of each one separately. So let's go back to the problem. I'm going to need someone to help me here. I put a problem up earlier and I said, hey, imagine if we were asked to take derivative of this. The function was, it was real ugly, and I wrote it down and I put a sad face. What was the original function? Anyone write it down? No one write it down?
4x cubed.
I'll make it up then. I'm going to make a new one up, all right? So how about this one? 5x to the 7th minus 8x to the 4th plus 3x to the 2nd minus x plus 8. Can you imagine trying to find the derivative of that with the limit definition? No, right? That limit, h goes to 0, all that would be such a nasty thing to have to do. But now, right, if I want the derivative of this function, what I'm going to do is look and see that I have 1, 2, right? I have pluses and minuses. So I have 1, 2, 3, 4. I have 5 terms, right? 5 terms. And I can differentiate them term by term because that says I can. So I'm going to take the derivative of this guy. Let me see. How do I want to write this? Minus the derivative of this guy plus the derivative of this guy minus the derivative of this guy plus the derivative of this guy. Right? I mean, that's, oh, I forgot the prime on this one. Right? That's essentially what that rule says, right? I can do them one by one. All right, so what's the derivative of this one? 35x to the 6th power. So the 7 comes out. The 5 comes for the ride, right? The 5's coming for the ride because it's attached to the function. So 7 comes out, hits that. I get 35x to what? 6. Okay, minus here. 4 comes out, hits the 8. 32x cubed, all right? Plus 6x minus 1 plus 0. Derivative of 8 is 0. See, that's a constant by itself. No function attached to it. Now, you know, this 8, there is a way you can actually convince yourself that the derivative of this is 0 with the power rule. Watch, next to this is an x to the 0. Do you believe that there's an x to the 0 next to that? Now use the power rule. It's 0, right? Does that make sense? Like, I just bring the 0 out, it's gone. You don't need it, but you know, whatever. This is it. Boy, that was a lot easier, wasn't it? Yes?
Is it supposed to be 35 or?
What did I, oh, why did I put 36? I don't know why. Thank you. Thank you. There's something going on with my arithmetic lately. It's been a rough week. Nice, huh? All right, so now let's do another example.
Can we do that one again?
What do you mean?
Take the derivative again?
Oh, you could, yeah. If I asked you for the derivative again, yeah, let's do it. What's f double prime? So look at that notation. If I ask you for the second derivative,
210x to the 5th
is it 210? I'm going to trust you on that. 210x to the 5th
minus 96x squared
minus 96x squared plus 6. No, nothing, right? Could we do it again?
Sure.
How many times do we have to do this before we get to 0? Wouldn't this eventually vanish to 0?
5 more times.
Yeah, because each time you take a derivative of a polynomial function, this is a polynomial function. Each time you take the derivative, the power comes down, right? Started with the highest power was x to the 7th. On the first derivative, the highest power is x to the 6th. Second derivative, x to the 5th. And it keeps on getting lower and lower, and eventually you get down to 0, right? That's only for polynomials. That's not for all functions in general. Sometimes when you take derivatives, the derivative is more complicated than the original function. Okay? And it's just polynomials behave very nice, though. They vanish away eventually. How about this one? F of x is x to the 4th minus 3x squared minus the square root of x plus 1 over x cube root of x. I promise you a problem like this on your test. Promise. It's going to be like this. When I test power rule, when I test my students to see if they understand power rule, this is the type of problem I give them. So let's think about this for a second, right? Right now we know how to take derivative of a constant by itself. We know how to do x to any power, right? We know how to do a constant in front of any function. We know how to do the sum and difference of functions. We can break it up. Have I given you any rule at all up to this point that allows you to deal with the derivative of a quotient when you have something divided by something else? Have I given you anything? No. So have I told you at all that you can just do the derivative of the top and then the derivative of the bottom separately? Have I said that? No, and that's not the case. With division, it's not the case. So you can't do that, all right? The biggest mistake I see people make on a problem like this is they'll give me this answer. 4x cubed minus 6x minus 1 over 2 root x over 1/3 x to the negative 2/3. Now I went fast here, but just see what I did. Derivative of this, right? Derivative of this, and then derivative of that. And then derivative of that's 0, right? So the top is, I just took the derivative of the top, and then this is x to the 1/3, right? X to the 1/3. I brought the 1/3 out and then subtracted 1. So I did the derivative of the top and bottom separately, didn't I? Yes? It's wrong. Completely wrong, all right? Can't do it. I will give you a rule. Next class, it'll be called the quotient rule, and that's the rule you have to use when you want to do division, all right? You got me? So how are we going to do this? Why would I give this problem to you if you can't do it? Well, the key to this problem is the fact that I gave you one term in the denominator and multiple terms in the numerator. And because there's one term in the denominator, you can use properties of fractions, and you can split this up into 1, 2, 3, 4 fractions, as shown. You can do x to the 4th over the cube root of x. Let me write it this way. Minus 3x squared over the cube root of x minus the square root of x over the cube root of x, and then plus 1 over the cube root of x. That's a property of fractions, isn't it? It's kind of like a backwards property of fractions. If you have a bunch of fractions, right, that have the same denominator, you can put them together, right? And what you wind up doing is just adding up all their numerators. So if I go from here to here, I think most of you are comfortable, right? Because they have the same denominators, I go to here. But I'm going backwards. I'm going from here to here. Now, each one of these can be written as a power of x, because this is really x to the 4th over x to the 1/3. Let me just keep going. Minus 3x squared over x to the 1/3 minus x to the half over x to the 1/3 plus 1 over x to the 1/3. We got them all? Where? No, because I haven't moved it, right? I'm leaving it on the bottom. It started on the bottom. That means the power on it is positive while it's down here. Now, if I wanted to move it up, it would become negative. Y'all probably don't even notice this, but this has always bothered me as long as I've been doing this, which is for a long time. Sometimes I write my fractions like this, and sometimes I write them like that. You see the difference? 1/2 and then 1/3. And there's no consistency, there's no rhyme or reason, just sometimes I do it one way, sometimes I do it the other. I don't know why, never been able to figure out, my brain just puts down whatever it puts down. But anyway, okay. Now what I'm going to do, there's no derivatives yet, right? Nothing, no differentiation has occurred yet. All I'm doing is algebra at this point, right? I'm just rewriting the original function. And now I'm going to use the very important property from college algebra that x to the n divided by x to the m is equal to x to the n minus m, right? That's the property. You subtract exponents when you're doing division. So this becomes x to the, all right, I have to take 4 and take away a third, right? 4 and take away 1/3. I have to get a common denominator.
3 and 2/3.
So what is it?
3 and 2/3.
Oh, okay, I'm not going to write it as a mixed number. I'm going to keep it as an improper fraction. So just 11/3? Is that okay? Yeah, in calculus, so you were saying this is 3 1/3, right? Do you all agree that 11/3 is 3 1/3? Okay, just erase this from your mind, okay? Mixed numbers are for like elementary school. Once you get past once you get into calculus, we just don't do this anymore. And there's a reason why. It doesn't lend itself well to the power rule, right? If I put 3 1/3 up here and you have to bring it down and subtract 1, do you see that it's just easier to work with the improper fraction. Also, a lot of people don't know what 3 1/3 means. It's just bad notation. 3 1/3 really means 3 plus a third. But with our notation, don't we always say when you put things next to each other, it's like multiplication? You see what I'm saying? Like, it's just, I wish there weren't mixed numbers. I just wish there weren't. It just adds a layer of crap we have to unexplain later. Just get rid of it. Know that it's there, but don't go to it. Always leave it as an improper. All right, what's our next one? Minus, what about this 3? The 3 comes. And all I'm doing is this right here. So 2 minus a third? 5/3. God, that looks terrible. Okay, x to the 5/3. See, I want to do that one that way. I don't know why. I just want to write it that way. Okay, what's 1/2 take away a third? Ooh, got you. 1/2 take away a third. 1/6. You know, there's a quick way to subtract fractions, right? You do multiply that times that, you get 3, minus that times that, you get 2, and then multiply the 2 bottom ones, you get 6, and that's going to be 1/6. That's the fast way if you're having trouble with it. So this is x to the 1/6. And then what's this last one? Yeah, you could look at there being an x on top, but don't overcomplicate it. Why don't you just bring that up? Bring x to the 1/3 up. So it would be x to the negative 1/3. Okay? There's no calculus up to this point, right? This is all just rewriting it. We look at it, we say, crap, we don't have a rule for doing a quotient or a division. We can only do x to powers. But there's one term, so we split it up. One term in the denominator, so we split it up, right? Then we rewrite everything, get our powers, and now we have something we can take the derivative of. So now the derivative. So the derivative of this, f prime of x, equals, all right, what about this one? Power rule, right? I can do these one by one. One by one. So do the power rule on this. What comes out front? 11/3. X to what power? 8/3. So you're subtracting 1 from this. So you're subtracting 3/3. 11 minus 3, 11/3 minus 3/3 is 8/3. Yes? 8/3 here. And then, see the minus here? I'm going to bring the minus, and then this is going to come out and hit that. Oh, that's nice, isn't it? 5/3 hitting a 3. The 3's cancel, and you just get 5. Do I need to write that down? So minus 5. X to what power? 2/3. All right, look at this one. Minus is here. Bring that down. 1/6. X to what power? Negative 5/6. You're taking 1/6 and you're subtracting 6/6. That gives you negative 5/6. And then last one here to here. What happens there? Because this is negative, right? And that's a positive. So when I bring that out, it should turn to a negative. So I'm going to put this as a subtraction. And then 1/3 x to the, be careful, negative 4/3, right? Because you're taking negative 1/3 and you're subtracting 1. So you're taking negative 1/3, subtracting 3/3. So it's negative 4/3. There it is. That's your derivative. Okay?
Would we have to change?
Leave it just like that. Yeah. The only ones that you should be go and be ready to convert to the other form are the square root of x. That derivative is 1/2 root x. And the other one I said you should probably burn in that's negative 1/x squared. Those are the only two that I would say, yeah, if you get to your answer, just switch it. Get to this. Here, no. Especially if I wanted you to take a second derivative, right? You wouldn't want to switch it back to the radical notation and put things on the bottom and then have to go do the derivative again. You'd have to switch it back to this, wouldn't you? So just leave it. Okay, good. Do y'all have any questions or you understanding so far okay? All right, new one. That's, as far as the rules for this section, that's it for the rules for this section. Next section, we have a few more. But there's some things I want us to consider. What if f of x is the sine function, sine x? And I ask us to find f prime of x.
Cosine.
Cosine x.
Did it last time.
Yeah, he's always.
I told you it was cosine, right? But I just told you. How would we prove that the derivative of that's cosine? Well, you could graph it, but if we can't rely on the graph too much because we were just estimating. We'd have to go to the good old definition, wouldn't we? What would the derivative of this function be? By definition, it's the limit as h goes to 0, right? Of f of x plus h minus f of x. Do y'all see that we don't have a rule to deal with this right now? Like this, sine of x is not x to a power. Right? So we don't have anything to deal with this. Right now, if we have x to powers, we're in business. But if we don't have x to powers, we're not in business, right? So I need to set this up. This will be the limit as h goes to 0, right? What happens when I plug x plus h into this? I get sine of x plus h, right? Minus f of x, sine of x, all over h, right? That's what I get. Now, sine of x plus h is not sine of x plus sine of h, right? That in pre-calc, that was never the case. You can't distribute sine through, sine is not like a number, it doesn't distribute. This is sine of this. So that's not true, but there is a formula for this. There is a formula. If you go to your formula sheets, if you remember